Welcome to this afternoon's Spark in AI Summit General Session. The resurgence in interest in deep learning can be traced back to record-setting models in computer vision and speech recognition almost a decade ago. Now, deep learning is finding its way into familiar enterprise applications, including natural language applications. We're lucky to have Kim Hazelwood with us today. She's currently the West Coast Head of Engineering at Facebook AI Research, and she'll discuss recent applications of deep learning to personalized recommendation systems. So give it up for Kim Hazelwood.
Okay, thanks so much. As mentioned, my name is Kim Hazelwood from Facebook AI Research. There I work with an amazing set of engineers, scientists, researchers who are passionate about the intersection between systems and machine learning. And today, on behalf of the entire team, I want to talk to you about an often overlooked space within machine learning and systems. First, let's take a look at how we got here. Over the past 20 years, we have seen a fairly significant increase in investment in deep learning. Now, a lot of that has come from fairly significant advances, algorithmic advances, that have really driven new use cases. Now, a lot of those algorithmic advances have been empowered by fairly fundamental breakthroughs at the systems layer, be it hardware, software systems. And then on top of that, we now have access to significant amounts of data, better quality data, as well as the tools needed to be able to aggregate and procure that data. So now let's also take a look at the end-to-end machine learning execution flow. So we essentially have three stages of the machine learning pipeline. We have the data stage, we have training, and then we have inference. In the data stage, we're taking unstructured data and structuring it into features. In the training stage, we're taking those features and determining how much do we care about any given feature and building out better models. Once we're happy with the model, we may deploy that out into production or to users. And that in and of itself produces additional data that we can use to advance the models that we've developed, continuing the cycle. So what I'd like to do is talk a little bit about each of those three stages and the scale at which we're facing each of these stages at Facebook. So first, let's take a look at data. So if we look at over the past year, the amount of data from our data warehouse that is feeding ML models, that went from 30% of all data driving machine learning models up to the current state of 50% of all data. And then on top of that, the amount of data that we've had doubles every year. So over a 1 year span, if you're doing the math, this ends up being a 3x increase in the amount of data that we're using for machine learning over a single year. Now, if we take a look at training, first let's look at people. So the number of engineers who are training models as their day job each and every day has doubled over a 12-month span. The amount of models that they're training has increased by 5x over that same time duration. And then the amount of computational capability needed to be able to power all of that machine learning training has increased by 8x over a 1 year span. And then how about inference? So each and every day at Facebook across all the family of products, we're doing hundreds of trillions of predictions across all products. These may be translations from dozens of language pairs to other language pairs. They may be detecting objectionable content and removing hate speech from our platform, or detecting fraudulent accounts, which our automated systems do each and every day, catching millions of fake accounts. So now let's talk about the machine learning models that power all of that, all of our products. Many people have a fairly simplified view of the world when it comes to machine learning, where the focus is either on computer vision or natural language processing. So we get a lot of questions along the lines of Do you care more about CNNs or RNNs? But the reality is that at Facebook, the picture is much more diverse, and we have a wide variety of models in use, some of them not even in the category of deep learning. And in fact, if you look across all of the various use cases, we have a pretty heavy focus on MLP across all of our ranking and recommendation products. So it's that recommendation space that I want to talk to you about today. So what are we using recommendation for? Well, we're using it for all sorts of use cases. If you take a look at your Facebook news feed, we're using recommendation to determine from the thousands of candidate stories we could have showed you, which ones are you most likely to like and engage with. When it comes to stories, which is across many of our products, we have lots of options that we could have shown you. How do we choose which ones are you most likely to like? And then Instagram itself, if you're searching, knowing what kinds of images you like to see, this is all powered by recommendation systems. So let's talk about the compute footprint that is powering all of those systems. So if you look across all training at Facebook, over half of it is training recommendation models. And then if you look at the deployed models we have in production, over 80% of our computational resources are being spent making predictions for recommendation systems. Meanwhile, if we take a look at the research community, you'll see a fairly different picture. So what we did was looked at the top system conferences for the past 5 years and took a look at what areas of ML were they focusing on, what were they designing systems for. And there we noticed that computer vision really took the cake. So most people were working on developing systems to recognize cats and dogs. Over 82% of publications were focusing on that. We saw 16% of publications were focusing on natural language processing, and then a mere 2% were focusing on recommendation systems. So what's going on? Why is there such a disconnect between what is happening in reality and in production and what researchers are focusing on in the community? Now, before we uncover that, first let's sort of run through what are recommendation systems doing from a high level. So if you think about the scale at which we're dealing with recommendation systems, we're dealing with hundreds of thousands of items that we're trying to decide how to rank in order to make a prediction about what should be the item that we show a given user. So we start from hundreds of thousands of candidate items. We're sending it through a neural recommendation model, which has billions of parameters. We're then coming up with this ranked list. And then that list is going out to users, and the scale of users at Facebook is in the billions. Let's take a step down and take a look at how do those recommendation models work from an algorithmic standpoint. So the thing to know about recommendation systems is they're leveraging two different types of features. They're leveraging dense and sparse features. Dense features for all of the continuous information that we have, and sparse features for all of the categorical features. And the way to think about continuous features is these are questions that have a concrete answer, and then categorical and sparse features are a vast number of yes or no questions about the user or about the items that we're trying to recommend. So the way we represent the continuous features, we send those through a dense DNN NLP like you're expecting. When it comes to the categorical sparse features, there we're leveraging embedding tables. And this is just a representation of all of the sparse data. We then need to take those two different components and integrate and combine them into a singular DNN. And coming out of that singular DNN then is a set of predictions across, for each individual item, what is the likelihood that the user will like this, and then we can form a ranked list from that. And this allows us to come up with a recommendation for what the user might like and recommend a book or an article of clothing or a photo. So when it comes to evaluating those recommendation models, there's a couple things we need to keep in mind. So number one is it's widely known that ranking more items leads to better recommendations. Therefore, from a systems perspective, what we want to focus on is very high throughput. We want to be able to evaluate lots of different candidate items all at once. At the same time, there's a user waiting on the other end for that recommendation. Therefore, we have a pretty firm latency requirement so that they're not left waiting for that recommendation to the point where they don't care anymore. So the way we evaluate and the way we optimize our systems is that we're focusing on latency-bounded throughput. Now, when it comes to how those recommendation systems are hitting the hardware or hitting the underlying systems, it turns out there's some fairly unique challenges when you focus on recommendation systems. So I'm going to talk about 3 of those challenges. First, I'm going to talk about the embedding tables themselves and the stress that introduces into the system. Next, I'm going to talk about how the recommendation models themselves have a wide variety of features of axes that they will vary, and how they execute on the underlying hardware will vary. The performance will vary depending on the features of the specific model. And so I'm going to talk about each of these systems challenges in turn. So first, let's take a look at the embeddings themselves. So the embeddings are very large. So these are orders of magnitude larger than anything we're used to seeing if we're focusing on CNNs, RNNs, or fully connected layers. So there we have to deal with pretty significant challenges to our storage hierarchy and how we optimize for that. On top of that, because we're dealing with sparse data, the computational intensity is actually quite low. It's a lot of zeros. It's not particularly computationally intensive to multiply lots of different numbers by zeros. So the overall flops per byte is significantly lower for embeddings than we're used to seeing in CNNs and RNNs. And then finally, because the data is so sparse, the access patterns throughout memory are going to also be very irregular. And this is pretty challenging to deal with from a systems perspective. Next, if you take a look at the models themselves. So if we took a look at 3 different recommendation models that are in use at Facebook, and it turned out those recommendation models varied significantly in some of the fundamental traits that they had. So across the 3 recommendation models, you would have fully connected layer sizes varying significantly. You had the number of embedding tables would vary, the size of those embedding tables, how often we're accessing those embedding tables would vary significantly across 3 different recommendation models. Then if we start to take a look at the bottlenecks that get introduced by each of these recommendation models and hone in on the specific operators that where all of the time is being spent, that also was varying across different recommendation models to where you can't even just go in and optimize for a very important operator because that's going to be different between the different recommendation models. And a lot of that had to do with some of the characteristics of how the recommendation systems were set up. And then finally, the sensitivity of those models when it came to how they would perform on the underlying systems, this also would vary, and it was very sensitive to any minor change we would make, like batch sizes, would swing which hardware system was better optimized for that particular model. Therefore, it it's extremely important that both the model itself and the underlying system are co-designed, designed together so that you can optimize for the specific bottlenecks that are going to come into play, and that you define your batch sizes according to what the underlying system prefers. Okay, so let's go back to my earlier point about what's going on in the research community. Why is everybody writing papers about recognizing cats and dogs when we have a fairly important problem on our hands on how to design systems for recommendation models? And I've already outlined a long series of challenges that need to be solved in that domain. So if you think back to what's different about computer vision and NLP domains, you'll get a little bit of a clue if you take a look at how they were able to evaluate any new ideas that they had. So it turns out one of the key enablers to doing research is having an agreed upon standard set of workloads and data sets that everyone can agree upon and can optimize for. And in the CV and NLP communities, we had those. But in the recommendation world, recommendation is extremely sensitive to the data set, and a lot of the data sets are proprietary. So this made it extremely challenging to even work in this space. So it's not that the researchers didn't think it was an important problem, it was that they didn't have the tools, techniques, and data that they needed. So that's why I'm excited to talk about DLRM. A year ago, Facebook released DLRM. This is the Deep Learning Recommendation Model. What this is a configurable model where you can change lots of different parameters about the type of recommendation that you're trying to do. The ratio of dense to sparse features, the widths and depths of your DNNs. All of these can be varied so that you can get a good sense of how sensitive are your systems to the types of variables that will change across recommendation models. And so that has been open sourced. It's available on GitHub. And then on top of that, there's also a industry-wide effort to standardize the workloads and the data sets needed to be able to evaluate systems in the ML community. And that effort is called MLPerf. This is a fairly widespread effort across nearly 50 companies and dozens of universities. And the latest release of MLPerf includes the DLRM benchmark, and it also includes a non-proprietary data set, ads data set that can drive the DLRM model. So now we have all of the ingredients that we need to be able to kickstart research and advances in the recommendation community. So hopefully throughout this talk, I have convinced you that recommendation systems are important. It's over 80% of what the computational cycles at Facebook are used for. Also, they're underinvested. Only 2% of the recent publications coming out of the systems community were focusing on recommendation systems. And at the same time, they have a set of unique challenges, lots of problems that need to be solved. And so that's why it's very important that we're remedying this underinvestment and that we have more people working in the space. And to be able to enable that, we are excited that now there are standardized benchmarks, workloads, and data sets available for the community to be able to leverage. Okay, so thank you so much for your time. And if you'd like to learn more, feel free to check out the Facebook research website where we have lots of publications. You can download the DLRM recommendation model from GitHub, and you can contribute to MLPerf or compete in the MLPerf competitions. Thanks so much.
Thank you, Dr. Hazelwood. It will be great to see how deep learning continues to evolve. Our next speaker is one of the pioneers in the field of digital forensics, which now finds itself at the center of the battle against deepfakes. UC Berkeley professor Hany Farid will give us an overview of the creation of deepfakes, and he'll describe emerging techniques for detecting them. Please join me in welcoming Professor Farid to Spark and AI Summit.
Thank you. It's good to be here. I'm going to talk today about deepfakes. It's probably a term you've heard about. But before I dive into deepfakes, I want to just give you a little bit of history of photo manipulation and media manipulation. And it is not something new. And arguably, we've been manipulating images and photographs as long as photography has been around. Stalin, for example, famously airbrushed people out of photos that fell out of favor. But really, starting in the 1990s, we started to see a revolution in digital imaging. And much of that has been driven by digital cameras, ubiquitous computing, and of course, programs like Adobe Photoshop, which have made it easier and easier to alter and manipulate photographs. And so in this 25-year period, we saw this rise of photo manipulation. And in 2015, we started to be able to do some pretty fun things with photographs like this. Where, for example, we would swap President Obama and Michelle Obama's face, and relatively straightforward to do this in a program like Photoshop. And we've also started to be able to manipulate videos in the mid-2000s and do things like this.
I appreciate the tenor of the conversations. I think it will actually yield results before the end of the year, and I look forward to continuing this dialogue in the months ahead. Thank you very much, everybody.
By around the mid-2000s, we've already started to see photo and video manipulation. In many cases, they were like the two last images and videos that I showed you, which is sort of for fun. We wanted to be able to poke fun or have humor or spoof presidents, for example. But since 2015, we've started to see a new age of digital manipulation, and that's what we're going to talk about today, so-called deepfakes. So if you navigate to the website, thispersondoesnotexist.com, true to the name of that URL, you will be presented with a face of a person, well, who doesn't exist. So these 6 people that you see here were completely 100% synthesized by a computer algorithm. They don't exist, and you can see that they cover gender, race, age, facial hair, glasses, and computers can now whole cloth synthesize images and, as I'll show you in a little bit, video of people who don't exist or people doing things that they never did. And this is a bit of a game changer, and that's what we're going to talk about today. So let's talk about how this person does not exist works. So this is these are created with a so-called GAN, a generative adversarial network. And here's the basic workings of how it works. Up in the top, you start with a random image. And when I say random image, I literally mean you drop down a bunch of pixels into an image. And that goes into a generator. That's the generator's responsibility is to create the image of the person who doesn't exist. And so it takes that image of random pixels and it hands it to a discriminator. And the discriminator has access to images of, well, people, actual people. And the discriminator's job is to ask, can I distinguish that image provided to me from the generator from these images of actual people? And in this case, the answer is, of course, yes. And so it goes back to the generator and says, please try again. And the generator makes modifications to those pixels, sends it back to the discriminator checks again, and it does that millions and millions and millions of times in a very tight loop, very, very rapidly. And this is why it's called a generative adversarial network. Generative because it's making something, adversarial because you're pitting that generator with the discriminator, and network because the underlying mechanism for the generator and the discriminator is a so-called deep neural network. And when you run this simple mechanism in millions and millions of iterations, it will eventually create an image where the discriminator will look at and say, yep, I can't tell that this is not a person, and now you have this person does not exist. Now, we can do something a little bit different with this. We can change identities with the same basic underlying mechanism. So now, let's say I want to change one person's identity in the top left here to another person's identity, let's say Steve Buscemi. So the generator's job is to modify pixels in the face, hand that to the discriminator, and the discriminator's job is not, is this a person? The discriminator's job is now to ask, is this Steve Buscemi, or whoever's identity you want to swap? If the answer is no, it sends it back to the generator, and again, they work in a very tight loop until the generator makes modifications that the discriminator cannot detect. And then when you do that, frame after frame after frame in a video, you get something that looks a little bit like this.
I expected Amy to win, so I just like, it was just, this was very truly surprising for me.
So what you're seeing on the left is the original video, Jennifer Lawrence, of course, accepting an award. And on the right is a so-called face swap deep fake, where on every frame, again, a generative adversarial network made the modifications that I was just talking about to replace Jennifer Lawrence's face with Steve Buscemi's face. And again, the power of this technology is that it is fully automatic. You provide the content that you want as original source, you provide the images of the face you want to swap, and the computer takes over. So there's no Photoshop, there's no After Effects, there's none of the skilled labor that is typically required to do this. And so let's look at a couple of examples of the things that you might be able to do with this type of face swap deepfakes.
She and Obama stole my microphone. They took it to Kenya. They took my microphone to Kenya and they broke it, and now it's broken. And you hear that? It's picking up somebody sniffing here. I think it's her sniffs.
So, of course, that's Alec Baldwin on Saturday Night Live, and what we've done is replaced his face with that of President Trump's, and you can now see the power of this technology in the ability to make it look like one person is saying something or doing something they never did. Let me show you just one more example.
Listen, America, Donald Trump cannot be president. He would be a disaster, a failure, a complete F. And America, you deserve better than an F. So on November 8th, vote for me, and I promise I will be a stone cold B.
So those are so-called face swap deepfakes, where you've taken one actor or impersonator and you've replaced one face with another face. And you can see the power of that technology to impersonate a president, a candidate, a CEO, whomever you like. Now, this is a slightly different type of deepfake, and I just want to mention it because we're going to be talking about it a little bit in a little bit. So let's go ahead and watch this, and I'll explain what you're seeing.
Now, you see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele. This is a dangerous time. Moving forward, we need to be more vigilant with what we trust from the internet.
Okay, so what you're seeing there is a fully authentic video of President Obama, but what you're hearing is Jordan Peele. And the manipulation now is not replacing an entire face, but simply synthesizing the mouth to be consistent with a new audio track. And again, this is a very similar type of, the goal is very similar, which is to create a video of a person saying something they never did, but the underlying mechanism is slightly different because we take an original video and modify only the mouth and the speech. These are so-called lip sync deepfakes. And so where do we worry about this type of technology? Obviously, lots of fun things you can do with it. They're highly humorous and for political commentary, but there's also a darker side to this technology. And where we are seeing the biggest harm today is in the form of non-consensual pornography, taking one person's likeness and inserting it into sexually explicit material and then distributing that on the internet. And that is probably today the most common use of deepfake technology, which again is yet another example of the weaponization of technology against women, and something that I think we need to get a handle on. Coming up into the 2020 elections here in the US, we are very concerned about misinformation campaigns in all forms, and one of them is in the creation of a video of a candidate saying something inappropriate or offensive and how that might affect an election. Obviously, in the courts, as we begin to rely more and more on digital evidence, can we trust body cam footage? Can we trust surveillance footage? Can we trust footage taken from an iPhone if that footage can be manipulated? How do we get our handle on evidence in courts of law? There are huge national security implications when we rely on video of events happening around the world to make life-altering global decisions. And of course, in the form of fraud. So what happens, for example, when I create a video of Mark Zuckerberg saying that profits are down 10%, I leak that on the internet, I can manipulate the stock market to the tune of billions of dollars before anybody else figures out that it's fake. So when you have the ability to make people say and do things that they never did, you can see that you have this long list of potential threats. And the things that we want to think about are now, how do we protect against that? From a policy perspective, from a legal perspective, from an education perspective, and from my world, from the technology side. And what I'm going to talk about next are some of the technologies that we are developing in order to detect these types of deepfakes so we can protect ourselves against a long list of potential threats. Let me start by way of motivation. I'm going to show you a series of clips of President Obama, and just pay attention and see if you notice anything, yeah?
Hi, everybody. 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 Hi, everybody.
So those are all separate clips of President Obama at the beginning of his weekly address. And what you probably noticed is that whenever he said, hi, everybody, he tilted his head up and to his right. So, hi, everybody. Hi, everybody. And what you may not have noticed, but you can see it on this frame right here, is that when he comes down, he purses his lips and he starts talking. And it's really consistent. He does this over and over and over again. And it's sort of like a mannerism, a behavioral tick that he has, and we all have it. The way I raise my eyebrow when I emphasize something, for example, or the way I turn my head when I talk. And we're going to use those mannerisms to try to detect deep fakes. So let me show you an example of that. So what I'm showing you in the top row is one frame of an authentic Obama video. And that graph that you see is showing two things. Along the horizontal axis is time. That's about 10 seconds of video. And on the vertical axis, I'm showing you two motions that he makes. One in blue is how he rotates his head up and down along the horizontal axis. And in orange is how he turns down the sides of his mouth as if he's frowning. And these are computed, averaged over hours and hours of video of President Obama speaking. And what do you notice? They're correlated. So when he turns his head down, he tends to frown, or when he frowns, he tends to turn his head down, and vice versa. And you notice this when President Obama speaks, when he's delivering bad news, sad news, when he's upset, when he's angry, he tends to frown, and his head turns down ever so little. It's a tell, it's a mannerism, it's a tick, if you will. Now, below what you're seeing is a lip sync deep fake, similar to the Jordan Peele video that I showed you earlier. And what do you notice here is that they're decoupled. Well, why is that? Well, in this video, the mouth is saying something, whatever the impersonator wants him to say, but the head is saying something else. The head doesn't know what the mouth is saying, and so we've decoupled and we've disrupted the mannerism that is typical of the way President Obama speaks. Now, that's President Obama's mannerism. That's his tell, that's his tick. Other people have different ones. So here, for example, is President Trump on the top, and now the blue corresponds to the chin pucker, and the orange corresponds to how wide the mouth is. And you see here that they are decorrelated. So when he does that chin pucker, his mouth is closed and vice versa. On the bottom row is Alec Baldwin, who does a very funny impersonation on Saturday Night Live. And here you can see that those two mannerisms are now coupled, they're correlated. So Alec Baldwin took two ticks of President Trump, the chin pucker and the mouth open, and he created a caricature of it, but he did it wrong. He got the dynamics of it wrong, and so we can use that to detect that something is wrong with the video. Okay? And everybody's different. Elizabeth Warren, Hillary Clinton, President Trump, President Obama, Vice President Biden, they all have different mannerisms, and what we do is we learn them. And we learn them by looking at hours of video of each of these individuals, extracting those patterns, and then using that to identify whether somebody's impersonating them through a deep fake. Okay? So let me show you just very quickly how we do that. So we start with the video, and we do some basic head and face tracking. So that blue box you're seeing is telling me the three-dimensional rotation of President Obama's head as he speaks. The green lasers coming out of the eyes are telling me where he's looking, and all the dots on the face are tracking his facial expressions. We take all of that information, and we extract 190 measurements, which I won't talk in detail about. And now I'm going to project those onto a two-dimensional space just so you can visualize them. So each dot in this graph here is corresponding to a 10-second video clip of Kamala Harris, Hillary Clinton, Elizabeth Warren, Cory Booker, and so on and so forth. These were obviously done at the height of the Democratic primary. And you notice a couple of things. One is everybody's off in their own corner. So all of the Obama videos are distinct from the Trump videos, which are distinct from the Elizabeth Warren videos. And so what that means is that when we now get a new video, we project it into the space and we simply ask, well, does this have the characteristics of Vice President Biden, Elizabeth Warren, Hillary Clinton, Kamala Harris, and so on and so forth? And then we can detect whether something is a deep fake or an impersonation. So that's one technique that we've developed, and you can see that it's very specific to an individual. Very good for high-profile people like candidates, but not so good for, well, people like me, where you don't have hours and hours of video footage where you can measure my various mannerisms. So this is good for doing things like protecting our elections, but not so good for the day-to-day run-of-the-mill people like me. So let's talk about another technique that we're developing. So what I'm showing you on this graph, on this figure rather, is a mapping between phonemes, the sounds that you make, and visemes, which is the shape of your mouth. So let's look in the bottom left-hand corner, MBP, mother, brother, parent. Try saying this at home. Try saying mother and notice that your mouth has to close. And now try saying it without closing your mouth. Try saying mother. Now, if you're a ventriloquist, you'll be able to do this. Everybody else, you will sound like you're not enunciating the word properly. My other favorite one is F and V in the top row. Favor, victor. Your lower lip curves in ever so slightly and your top teeth come down. Favor and victor. So when you make certain sounds, your mouth has to have a certain shape. This is the phoneme to viseme mapping. And when we create things like lip sync deep fakes, those mechanisms, that GAN that I told you about earlier, the generative adversarial network, doesn't know anything about phonemes. It doesn't know anything about visemes. All it knows is about pixels and these classifiers. And so we can leverage that ignorance in order to determine whether the mouth is making the proper shape to, say, a particular phoneme. So let me give you a couple examples of that. So what I'm going to show you here is a slow motion version of President Trump saying, I am. Okay, so let's go ahead and watch that video. Good, so you see him saying I'm, and now I'm going to just show you it in frame by frame so you can see what happens to his mouth. So frame 1 of 6, 2 of 6, 3 of 6, 4 of 6, 5 of 6, and 6 of 6, and now his mouth is entirely closed. There's that M phoneme, and then the viseme is correct. So this is an authentic clip. Let me show you now a segment of a lip sync deepfake where, again, he's saying I'm, and you're going to hear the beginning of the next word. So you're going to see I'm so, and I'm going to put in that S so you can see I'm closing off the phoneme M. So let's go ahead and watch this. Okay, now let's do it in slow motion again. 1 of 4, 2 of 4, 3 of 4, 4 of 4. So I'm so, and you can see his mouth never closed. And if his mouth never closed, something is almost certainly wrong because it's very, very difficult, if not impossible, to say mother, I'm, without closing your mouth. And so what we've been doing is building models of these phoneme-viseme matchings, pairings rather, and then going back in and making sure that the mouth has the proper shape and exposing things like lip sync deepfakes, which are simply ignorant of these types of mappings because of the nature of the way GANs work. So I've described 2 techniques that we've developed for detecting deepfakes, and I've described the threat of deepfakes, and I've described how deepfakes are made. And if you invite me back next year, almost certainly everything will have changed. The nature of the creation of deepfakes, the risk of deepfakes, and the detection of deepfakes is changing. It is a fast-moving field, and we have to start thinking seriously and carefully about the threat of misinformation. We are living through an unprecedented time where we are relying more and more on the internet for information that affects our health, our societies, our democracies, and our economies. And when we can't trust the media that we see, hear, and read on a daily basis, we are in trouble as a society and we are in trouble as a democracy. And while I focused on the technology, we also have to get serious about the policies. We have to get serious about the regulation. The tech companies that allow this misinformation and disinformation to proliferate through their networks have to get more serious about how their platforms are being weaponized. Our regulators have to get more serious about how to get control over mis and disinformation that is designed to sow civil unrest, tear societies apart, and disrupt our democracies. And we have to do all of that, by the way, quickly and with respecting freedom of expression and freedom of speech and a vigorous debate online about people who disagree. And I think that there is a middle ground there, but we have gone too far in one direction where we simply can't trust anymore what we see, hear, and read online, and we need to regain some trust in order to have a sound democracy, society, and economy. Thanks very much, everybody.
Thank you, Dr. Farid. Really great to learn how you're fighting the impact of deep fakes. This concludes our general sessions for today. Before you go to your next session, I just want to share a few final housekeeping items. It's not too late to explore the Developer Hub and Expo, visit our sponsor booths, and play Summit Quest. And as a final reminder, we hope you'll consider participating in our Summit donation matching program. Let's get to 100K. Thank you, and have a great rest of your day.
It's making me weaken. You and your stardust, walking like that. It's really getting too much, but I can't pull back. Though I try to resist, I can't fight this. And no one makes me feel like you do. And no one sets my body on fire. And no one gives me shivers like you. Oh, no one does it better. How I try to sleep, but you're deep in my mind. Got a hold of me. When I'm awake, I'm all blind. You and your magic, like infinite power. God knows I try to resist, but you're pulling me closer. Oh, I gotta stay away, but you won't let me.